So let's continue our discussion on the comparison theorems, and specifically what we're going to do now is define the limit comparison theorem, or the limit comparison test. And much like the direct comparison test, this has a very similar idea behind it for what exactly we're doing. So this is the limit comparison test. Again, it's just a test that we want to use here to help us, given maybe a very complicated function that we don't want to evaluate the improper integral of, we choose a different function that's kind of simpler but related to the complicated function, and we use that new function to determine whether or not the improper integral of a given function, the complicated function, is going to converge or not. So that's the point of this test and what it's doing for us. In exactly the same way as the direct comparison test, but it's a different test. So again, we're going to take two positive functions, let f and g be two positive functions. Also assume that they are continuous. From some value a to infinity. So on the entire interval from a to infinity. Again, this is the limit comparison test for improper integrals of type 1, just like the direct comparison test was for improper integrals of type 1. There are restatements of both these tests for improper integrals of type 2. I won't be going over those because they're very, very similar to the statements for improper integrals of type 1, just with a few slight changes. But so the idea then is that we have two positive functions which are continuous from a to infinity, and we have to assume one final thing, that the limit as x goes to infinity of the ratio of these two functions, so f of x over g of x, is equal to some value L, where L is between 0 and infinity. So not equal to 0, not equal to infinity, but L is some finite non-zero real number. So if this is the case, if these three things are true, then we can state the following. We have that then the improper integral from a to infinity of f of x and the improper integral from a to infinity of g of x either both converge or both diverge. So it's a very similar statement, in fact, to the direct comparison theorem. It's used similarly to the direct comparison theorem. But sometimes the limit comparison test is easier to use than the direct comparison test. So the idea then is that we have some function whose improper integral is very complicated to evaluate, so complicated that we don't want to really deal with evaluating the improper integral. So what we do is we find a simpler function. It's kind of based off of the complicated function, whose improper integral we know whether it converges or it diverges. And we use that comparison function, and as long as this is true, the limit of the ratio of these two functions is equal to L, where L is some value 0 to infinity, we know that these two functions' improper integrals are going to have the exact same behavior. They're either both going to converge or they're both going to diverge. So let's see this applied to a number of different examples. So what we'll do is look at one of the examples that we previously looked at already. And this is the example of the integral from 3 to infinity of 4 times x to the 1/3 over 5x plus square root of x. The idea here is that we already showed that this improper integral does in fact diverge using the direct comparison theorem, or the direct comparison test. However, what I want to do now is show how to do this instead using the limit comparison test. And remember that previous step that we did before, the starred step in the previous part, where we actually found that we expect this to diverge from the starred step, right, in the previous example when we do this with using the direct comparison theorem. This is that kind of rule of thumb method that isn't equivalent to doing the actual test itself, but is something that's important to do at the beginning of these problems to get an idea of whether you expect the integral to converge or diverge. I'm not going to repeat that process here because I already did it in the previous example, but definitely go back and take a look at that if you want to remember that. But this is what we're going to expect here. It's also useful to remember, and I'll scroll back up just to remember what we found from that process. From that process, we found that when for large values of x, this function is approximately equal to 4/5 over 2/3. So I'll copy this entire thing and bring it down. So this step is very important for us. I would argue that it's actually more important for us when doing the limit comparison test. This first step right here. We found that for large values of x is much larger than 1, say, our function, our unknown function, is approximately equal to 4/5 1 over x to the 2/3. So this is so important because this is the comparison function that we're going to use, right? Finding this function is kind of the key to what we're going to do here. What we're going to do is look at the limit as x goes to infinity of our function f of x over the comparison function. This is the limit as x goes to infinity of 4 times x to the 1/3 over 5x plus the square root of x divided by 4/5 times 1 over x to the 2/3. And so you'll remember from the statement of the limit comparison theorem, if this limit exists and is equal to a non-zero value, then the two improper integrals have to have the same behavior of both functions. So first off, we can rewrite this a little bit by bringing up x to the 2/3 to the top. So the 4's also cancel one another. So we bring together all these fractions. So at the top we'll have 5x to the 1/3 plus 2/3, which is just x to the 1, divided by 5x plus the square root of x. And lo and behold, if we do one application of L'Hopital's rule, we will end up seeing that this limit is in fact equal to 1. So just put that right here, which is non-zero, and it's also finite. So therefore, by the limit comparison theorem, the integral of f of x, which is 4x to the 1/3 over 5x plus the square root of x, must diverge. And this is because the simpler comparison function, the integral from 3 to infinity of 4/5 1 over x to the 2/3, diverges. And this is guaranteed by the limit comparison theorem. And so I'm not going to go over the proof of this theorem, even though it is rather clever. Same thing with the direct comparison theorem. The main idea here is that if this limit of the two ratios of the function is equal to a constant value, what this is saying is that as x gets larger and larger and larger, very large, the growth of the two functions is very, very similar to one another. They're growing at a very, very similar rate that only differs by a constant. And because of that, right, this is the main reason why we have this result. Because the growth rates of the functions just differ by a constant, then if one of the improper integrals diverges, then the other one has to diverge, and vice versa for convergence. Now, I want you to be very careful here. This limit has nothing to do with the actual value of the improper integral. So don't confuse that with the actual value of the improper integral. If you were to apply this test and find that a given improper integral converges, does not mean that you have the value of that improper integral. And you have to be very careful with that, because this is an issue that I think many students have when applying the limit comparison test, and sometimes even the direct comparison test as well. That these tests only give you whether or not a given improper integral converges or diverges. They do not give you the actual value of the improper integral. So please, please, please make sure to be careful of that. And that's so important that I'll probably write it down as a comment. I'll do one more example from yesterday, or from the previous lecture, and that's the surface area integral for Gabriel's horn. You'll remember from that example. So it's a few examples ago we calculated the surface area and the volume of this infinite shape, the surface of revolution generated by 1 over x, as x goes from 1 to infinity. So it's this infinite horn shape. And this shape is very interesting because it has a finite volume. It bounds a finite volume. Volume is actually equal to pi. But it has an infinite surface area. And we proved that it has an infinite surface area by going through and actually using the direct comparison theorem. We showed that this improper integral right here diverges. But we could also have chosen to use the limit comparison theorem to show that this diverges as well. A suitable comparison function, we would have to go through and figure out what exactly we want to use as our comparison function here. So I recommend that you kind of practice, go through and do that step here. But you should see very clearly that we can just choose the function 1 over x here for our suitable comparison function. And the reason is given by the following limit. So if we take the limit as x goes to infinity of our complicated function, this is our complicated function f of x. And then our simpler function is function 1 over x. Well, this limit we very quickly see that 1 over x's cancel out. And there's no dx here, sorry. The 1 over x's cancel out. And the limit of 1 over x to the fourth as x goes to infinity is 0. So this limit is going to be equal to 2 pi, which is non-zero finite value. So then by the limit comparison theorem, the surface area integral that we started with, this integral right here, diverges because the integral from 1 to infinity of the function 1 over x dx diverges, which we showed in the previous lecture. So this is a very, very neat and quick application of applying the limit comparison theorem to show that a given improper integral diverges. So it's very, very neat. And I think you can see that depending on the type of function, either the LCT or the DCT might be easier or more difficult to apply. For many functions, we could apply either of these two, but for every different example, you're going to have that maybe the LCT or the DCT might be an easier theorem to apply. It's really going to depend on the example. So we'll do one more example just to really kind of take this home and make sure everything is clear. So let's consider the improper integral from 3 to infinity of 6 plus the square root of x over x squared plus 7x plus 18. So does this improper integral converge or diverge? And again, all we want to do is start by using our kind of rule of thumb here to determine whether or not we think it's going to converge or diverge. Now, it's very important that you recognize this as a rule of thumb, and that you recognize we're not applying the actual limit comparison theorem yet at this initial stage. What you want to note is that for large values of x, the numerator here is dominated by the function square root of x. This is growing much faster than the function constant function 6. So our ratio here is going to be approximately, for large values of x, equal to the square root of x, or x to the 1/2, divided by the denominator, and in the denominator, this is being dominated by the function x squared. Because x squared is growing much faster than 7x and 18. So for very large values of x, the x squared term is really it's much larger than the other two terms in this denominator. So this fraction is approximately equal to this fraction right here. And this helps us because now we have that. This is equal to 1x to the 1/2 minus 4/2, or 1 over x to the 3/2. So we have that for large values of x, this function right here is approximately equal to 1 over x to the 3/2. And this is very, very useful now for us because this is telling us which function, which simpler function we need to use in our direct comparison, or sorry, not the direct comparison theorem, in the limit comparison theorem. So now that we've done this rule of thumb, and this is always a good idea to kind of do, even for the direct comparison theorem, as you saw when I went over that example, it kind of gives you an idea of what to expect, right? We know that the improper integral of 1 over x to the 3/2 from 3 to infinity, that improper integral is going to converge because it has an alpha value that's greater than 1. So therefore we expect that this improper integral that we're evaluating is also going to converge. And this is exactly what we see. So now at this point we are ready to apply the actual limit comparison theorem, or the limit comparison test. We're going to take our actual function, which is this ratio right here. So this is our f of x. And we're going to divide this by our comparison function, which is 1 over x to the 3/2. And this limit is going to then become, once we do a little bit of algebra to simplify, it'll be 6 times x to the 3/2 plus x, or square root of x, times x to the 3/2, which is x to the 4/2, or x squared, divided by x squared plus 7x plus 18. And then this limit can directly be evaluated and is going to directly come out to be equal to 1, which is a finite non-zero value. So therefore, by the limit comparison theorem, the improper integral from 3 to infinity of this function, 6 plus square root of x over x squared plus 7x plus 18, is going to converge. Because the improper integral from 3 to infinity of the comparison function, 1 over x to the 3 halves dx, converges. Right? This is one of those nice comparison alpha integrals, 1 over x to the alpha integrals that we talked about at the very beginning of the last lecture. Now, again, it's very, very important for me to point out that nowhere in this did we find the actual value of this improper integral. These tests only guarantee whether to show us that the integral, the complicated improper integral, converges or diverges. They say nothing about what its actual value is. So even though we can often go through and get the improper integral of the comparison function, this is not the same thing as the improper integral of the more complicated function. So keep that in mind. It's a very important limitation to these tests. But anyway, this will be the end of our segment on improper integrals, this lecture on improper integrals. I hope you had a fantastic day and that you learned something.